Hello everyone, welcome to our presentation. Today I will present Pangolin, an incremental hybrid fuzzing technique using polyhedral plus abstraction. This is a work from the Hong Kong University of Science and Technology and the Xiamen University, both in China. Let's start. So fuzzing is nowadays one of the most effective ways to detect vulnerabilities. For example, Google detects over 16,000 bugs with fuzzing in open source project. Heartbleed, one of the most impactful vulnerabilities in 2014, can now be detected in 10 seconds with leaf fuzzers. The benefits of automatically detecting vulnerabilities without much manual efforts make fuzzing more applicable for various scenarios. Meanwhile, fuzzing also appeared attention from academia. Since 2015, there are over 150 research papers published in top conference. We first surveyed the number of fuzzing papers published in the recent 5 years. This statistic shows the growing trend and popularity of fuzzing. Among these papers, hybrid fuzzing is one of the major directions in nowadays research. This is a workflow of hybrid fuzzing. Apart from conventional fuzzing, hybrid fuzzing applies symbolic or concurrent execution to generate input for those hard-to-cover branches. Therefore, fuzzing can cover more program paths with the guidance of constraint solving. However, hybrid fuzzing suffers from the efficiency issue. From the existing studies, we know that symbolic or concurrent execution is expensive to handle large-scale programs with enormous number of paths, while finding a feasible solution in constraint solving is an NP-hard problem. Overall, hybrid fuzzing could not achieve high coverage in large-scale programs. We analyzed the reason that existing fuzzing technique do not apply the incremental mechanism well. Incremental mechanism is designed for improving the efficiency, which has achieved a great success in other fields. However, in hybrid fuzzing, only seed input are preserved at the intermediate stage, which cannot support incremental mechanism well. For instance, hybrid fuzzing takes a huge time cost for collecting and generating a seed input for fuzzing. This seed input indeed increased the coverage for fuzzing successfully. However, after the execution, inheriting the concept of fuzzing, only the seed input is preserved while these expensive constraints are discarded directly. Thus, the intermediate state is only described by a single seed input, which cannot provide enough guidance for further input generation. This unawareness causes both mutation and constraint solving not efficient. We name this unawareness as not incremental for fuzzing, which first caused the mutation to be unguided. The key reason is that the seed input do not preserve sufficient intermediate state in hybrid fuzzing, which result in a low probability to generate feasible input. For example, for the following programs, fuzzing need constraint solver to generate the seed input for condition at line 3 due to the difficulties brought by the magic values 3 and 4. However, a seed for fuzzing is only a sequence of values which lose lots of analyzed results such as its path constraint, related grammar, or structure information. In this example, since the constraint for variable x and y is very strict, any mutation involving these two variables cannot produce the input entering the true branch of condition at line 3 to further explore the programs. Similarly, for variable z, even though there are some options for its value, the narrow range could still leave mutation ineffective due to the small probabilities, which waste the efforts of constraint solving. Thus, the lack of constraint preserving makes the random mutation unguided and thus deficient. The second problem brought by this non-incremental issue is the redundant computation in constraint solving, which need to solve the same constraint again. Using the same example as the illustration, after fuzzing reaching another uncovered condition at line 8, nested in the previous one at line 3, Fuzzing applies constraint solver again for another feasible seed input. We notice that part of the constraint are computed redundantly at line 3, which makes this process less efficient. Overall, both mutation and constraint solving, which is the main components of fuzzing to generate the new inputs, are thus deficient due to this non-incremental issue. With such observation, our idea is to preserve and reuse the constraint to support incremental fuzzing. To illustrate our goal, we attempt to build a new incremental mechanism in fuzzing to better preserve the intermediate states, which optimize the seed mechanism in fuzzing to improve both mutation and constraint solving. It can also be adapted to any other fuzzing framework. To achieve this goal, the first challenge is how to preserve the constraint as the intermediate states for fuzzing to reuse efficiently. Our observation is to interpret the feasible input search space of the given path constraint. So for each path condition inside the programs, it has its own feasible search space for the input. So if we can preserve the search space to guide input generation, then the efficiency should improve. Therefore, our intuition is to directly model the search space of the path condition with various polyhedral. Using the previous example to illustrate this intuition, for condition at line 3, if we can extract the feasible search space of the related variables x, y, and z with the precise intervals, then we can boost the success rate of generating a new input entering the true branch of the condition at line 3 from less than 10 to the power of minus 25 to 100%. We can find that those intervals can form a polyhedron describing the feasible input search space, which significantly improve the effectiveness. Therefore, for each uncovered condition detected by code execution, we attempt to infer its feasible search space for the input. This is a graphic expression of the search space describing the condition at lines 3, 4, and 8. We concluded that a path condition can be regarded as a set of lower and upper bounds of its related variables. We define the intervals for the related variables as the path abstraction, which describe the feasible search space of the input with the given path constraint. Therefore, path abstraction inference can be regarded as an optimization problem, which try to find the minimum and the maximum values for the related variables. In Pangolin, we leverage set-OPT algorithm to infer these bounds, which guarantee that all the feasible inputs are included in the search space described by the path abstraction. For each seed with analyzed constraint in hybrid fuzzing, we infer the path abstraction along with the seed's input to better describe the intermediate states for fuzzing. Next, we're trying to improve the effectiveness of mutation. Let's recap the challenge in the existing techniques from search space perspective. On the one hand, for constraint solving, it is good at generating feasible values. However, it is not efficient. On the other hand, mutation is good at generating general values. However, we cannot guarantee it is feasibility to reach the target branches. To generate the input that can reach the branches just founded by constraint solving efficiently, we find that the nodes received in the search space described by the path abstraction should be the feasible input satisfying the original path condition. Therefore, we attempt to sample the new input from the search space described by the path abstraction. Since we transform the input generation into node sampling, we leverage the state-of-the-art sampling algorithm Heqing, which is capable to sample nodes from any given polyhedral. It is also very efficient since the complexity is linear with the number of related variables to generate new inputs. Meanwhile, fuzzing should sample from uniform distribution. The uniform distribution increases the probability to cover the more dominant branches directly without further solving. For example, if we sample from search space of the condition at line 3 with centralized sampling algorithm, the input may not cover the branch at line 4 and 8 directly. Therefore, fuzzing still needs to apply constraint solving to cover these two branches. With uniform sampling, however, we could directly cover this condition without applying the constraint solver again. With the guidance of path subtraction, we can generate new input satisfying the constraint. We named it as constraint mutation. Next, we're going to solve the non-incremental issue in the constraint solving. For constraint solving, path abstraction can be reused for performing the infeasible path, using the control flow graph of the previous example as demonstration. Existing coverage-guided fuzzing should attempt to cover the edge CD. This causes constraint solvers always solving the constraint whenever the execution reaches these uncovered edges. However, we can notice that this path is always infeasible due to the contradictory of the path condition. Fortunately, with the path abstraction inferred at line 3, which is the simplified version of the prefix path constraint, we can find that this branch condition is conflicts with the prefix condition by verifying the satisfiability of the path abstraction conjunct with the uncovered branch condition, and thus this edge is filtered in the further fuzzing process. Moreover, path abstraction can be reused when solving the constraint for the nested condition. Since the path abstraction is the simplified version of the partial path constraint, we conjunct the path abstraction with the path constraint, which provides a smaller search space for solver to find out the feasible solution. And thus, the efficiency of constraint solving is improved. With path abstraction, constraint solving can prune the infeasible path while accelerating the solving performance. We name this process as guided constraint solving. Overall, we improve the original workflow of hybrid fuzzing in both mutation and constraint solving by incrementally preserve and reuse the previous computed constraint via path subtraction, which can be regarded as an advanced preserving mechanism compared with using the seed input. As for the evaluation, due to the time limits, we present some statistics to show the improvement brought by our methods. More details can be found in the paper. We evaluate Pangolin in 9 real-world benchmark programs, which are also frequently tested by the existing work. They maintain different functionalities. Overall, in these 9 programs, we found 41 bugs with 8 CVE assigned. In terms of the coverage, we compared our results with 3 state-of-the-art hybrid fuzzing, QSIM Driller and Angora, and 2 state-of-the-art gray box fuzzing, AFL Fast and AFL. We conduct 24-hour experiment 10 times with the same given seeds. Overall, we achieved 21.4 and 16.8% coverage increase compared with next to best fuzzing QSIM and Angora on average. We also provide p-value from statistic evaluation of these 2 fuzzers. The first p-value is compared with QSIM, and the second one is for Angora. Both values show the significance of our contribution. For individual contribution of the 2 methods, guided constraint solving and constraint mutation, we compared the time cost of original constraint solving with guided constraint solving. We conducted the experiment based on the constraint collected in the previous coverage experiment in 24 hours. We found that path subtraction can be reduced 20% to 30% time cost on average for constraint solving. For constraint mutation, we compare with the state-of-art SMT sampler, which samples directly from the constraint. We conduct the experiment on the same 9 projects. We record the average number of feasible input generated in 10 seconds for the past constraint collected in the fuzzing process. Overall, Pangolin can produce 93.78% more feasible input than SMT sampler on average. We also outperform SMT sampler on more than 95% of the individual constraints. To summarize, Pangolin compensates the weakness of insufficient seed-preserving mechanism to better support incremental fuzzing. Pangolin infer the path subtraction to preserve the constraint for both mutation and constraint solving. Meanwhile, the incremental mechanism brought by path subtraction can further provide opportunities to improve fuzzing with sophisticated sampling and incremental solving mechanism. We also believe that not only constraint, but also grammar and other program information could also take into consideration in future research. This is all of our talk. Thank you for your attention.